मेरी स्क्रीन शेयर दिख रही है सर?
हाँ, दिख रहा है, दिख रहा है।
वो पावर पॉइंट का स्लाइड दिख रहा है ना?
हाँ, दिख रहा है, दिख रहा है।
ओके।
सो अभी आप थोड़ी देर शेयरिंग निकाल दीजिए। थोड़ा हमें
हाँ,
चांस दीजिए कुछ बोलने के लिए, क्योंकि बाद में तो आपको ही बोलना है 3 घंटा।
नो प्रॉब्लम। नहीं, मैं सिर्फ देख रहा था वो कैसे दिख रहा है। फुल
हाँ,
स्क्रीन दिख रहा
हाँ।
है कि सिर्फ वैसे ही दिख
नहीं,
रहा है?
नहीं, फुल स्क्रीन नहीं दिख रहा है अभी।
ओके। ओके, ठीक है। नो प्रॉब्लम। मैं निकाल रहा हूँ इसको।
हाँ।
किधर गया?
अच्छा, हमारी सोनी मैडम लॉकड आउट हो गई।
तो 2 मिनट में आता हूँ मैं।
हाँ, हाँ, चलेगा। हम लोग अभी और 5 7 8 मिनट में चालू करेंगे, ठीक है।
हाँ हाँ, नो प्रॉब्लम।
ओके।
गुड मॉर्निंग.
हाँ, गुड मॉर्निंग मॅडम. मला वाटतं सरांनी शेअरिंग टाकल्यामुळे तुम्ही बाहेर निघून गेला, बरोबर ना?
नाही 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 सर, माझं इंटरनेट गेलं होतं माझं.
अच्छा, ओके, ओके.
पण मग ते त्यांनी काय केलं मला कळलंच नाही. आता इंटरनेट गेलं तर आता मी म्हंटल असं का होतंय, माझी माझी पॉवर पॉईंटचीच विंडो दिसते, मला काय आवाज येत नाही.
ओके. Govind sir, shall we start?
Yeah.
हम शुरू करें? Okay. I think we should go ahead.
Yeah, sure.
So good morning, everyone. Welcome to this 9th day of AICT sponsored 2-week online faculty development program on insights into intelligent automation, machine learning, and data science. So as you all are aware that this particular is on data science and its applications. So we have already studied the entire life cycle of data science, and now we are studying its applications. And today I am happy to introduce our speaker, Mr. Govind Gaundalkar, sir.
Thank you, sir.
Yeah. Soni madam, next slide. Slide is not changing. Okay. Okay. Thank you, ma'am. So I'm really happy and pleased to invite sir and welcome. He is on board. As usual, sir is always available before time. Before if session is at 10 o'clock, I was 100% sure and relaxed when I called Govind sir that he will be available at 9:45, and he was there. So thank you, sir.
Very much
Our
for
students
that
also
great
learn.
introduction.
Our students and everybody should actually replicate this punctuality. I am observing you from last 3 years, and you're so punctual every time. And today also you came before time. Thanks a lot. So sir is actually a certified trainer from Safety Systems Limited, which is from United Kingdom. It's a company based out of United Kingdom. It's a company of Dr. Michael Pond, who is a pioneer in embedded systems domain, and particularly in a domain related to safety and security and reliable design of embedded systems, and particularly automotive sector. So I'm really happy that a trainer who is certified from the Safety Systems UK has been associated with S.P.I.T from last 3 years, and such dedication is we have seen, and the knowledge and the zeal and the passion with which he teaches, you will automatically realize in today's morning session as well as tomorrow's entire session. So sir is a certified trainer at a level 1 from Safety Systems United Kingdom, UK. He worked various platforms related to embedded systems, starting from 8085 to the recent one, you just call it, and sir has worked on most of the systems. And sir's specialty, if you ask me, in an embedded domain, it is about a time-triggered, real-time embedded systems, which is not an easy task to design the applications based on time-triggered embedded systems. And probably he is one of the rarest faculty available in this region who works on the time-triggered systems, if I'm not mistaken. So welcome, sir. Welcome to this faculty development program, and we are looking forward for your today's session as well as tomorrow's session. So today's session is on TinyML, and I'm sure this is at least new keyword for me, and new learnings are going to happen for us. So welcome, and now the platform is yours for next 3 years.
Thank you, sir. Thank you very much for that great introduction of mine, and thank you for all the kind words. And first of all, I would like to thank you, sir, and S.P.I.T for inviting me for this FDP on machine learning and data science. And I am really grateful and happy to be here and discussing these things in this domain with all the participants of this FDP. Good morning, all. My name is Govind Gaundalkar, and I lead Microdevice Technologies and skillsuniverse.net.in. I'm basically more into time-triggered embedded systems domain, certified from Safety Systems Limited UK, and we Microdevice Technologies represents Safety Systems Limited in India for the time-triggered domain-related designs. It's basically about critical domains where such systems are used, like railways, aerospace, automotive, medical, and white goods. Safety Systems is owned by Dr. Michael Pont, and it's basically they are into designing such kind of systems, and they are actually authoring the basic standards for autonomous vehicles, and those may soon become, the standards all over the world. And that is what I actually do as a TT engineer. Uh, Today's discussion would be focused on TinyML. Currently, time-triggered architectures are not ported to this domain. This being a very, very new domain, and still work is on, and good amount of work is being done by Google on this using TensorFlow. So we are going to really focus on all these things today, and I'll give you the overall picture. We may not discuss any code in detail, but I will certainly show you some working examples for this. On a board, on an embedded board that is from ST Microelectronics, and we will see how it is. What are the? That will give you insights into what kind of applications can be possible with this particular interesting field that's coming up. And trust me, it's going to be the next industry when it comes to machine learning. So without any kind of further delay, let's dive into it straight away. And I'm just going to share my screen with you. I hope my screen is clearly visible to everyone. Okay, yeah. So let's start off. So basically, as I said, I lead Microdevice Technologies and Skills Universe Technologies. Basically, these are my two firms, and they are into different kinds of things. Microdevice is basically into time-triggered domain, and in Skills Universe, we do some different kinds of trainings, and we have been associated with S.P.I.T for those international certifications that we do in the time-triggered domain. Let's start. Today's topic is a glimpse into machine learning with small devices. And tiny is big and bright. That's the key word today. So tiny is big and bright. And what are these small devices? That's what we are going to see. And what this TinyML thing is all about. Many of you must have heard this term, and you must have started some activities on this. But nonetheless, let's have a look into what this amazing field is all about, and what we can do with it, what we can achieve with it. So to begin with, what is TinyML? TinyML is nothing but tiny machine learning. Now, tiny machine learning does not mean that the machine learning paradigm is small, or it's become small in size. It has an altogether a different meaning. TinyML is an emerging field, which is the intersection of machine learning and embedded systems. So basically, what we are doing is, or not we rather, it is all come up from the research of Google, and the way they have worked with TensorFlow. So it's come out of that. So basically, it's an emerging field which is being applied to embedded systems. So it's the intersection of machine learning and embedded systems. In TinyML, it's all about taking just a small little computing device and enabling it with machine learning. So TinyML actually works on devices that have a power budget of less than 1 millivolts. So you can see this is, I'm talking about devices like this. Now this is a board from, I hope you can see the board. Yeah. It is a board from ST Microelectronics. It's an STM32F4, basically a Cortex M4 device. I'm going to run something on this towards the end of this session. So this is what I'm going to use, and we are going to talk about such devices. Okay, so when I say devices, I mean devices like this. There is one microcontroller that is a Cortex M4 from ARM that's going to be used for this particular kind of work. And there are a host of other different processors that are possible. But we prefer working on the ARM architecture because we believe ARM's architecture is the future of this world when it comes to embedded domain or domains that are related to TinyML. So that's the best architecture to use today. It's a 32-bit architecture. And as you know, all these mobile phones that we use today, all of them use this ARM architecture, and they are the application grade microcontrollers, that is the A grade. And Qualcomm, you have various processors that Qualcomm produces for different kinds of mobile phones. And these devices are the ones that are actually working on the architecture produced by ARM. ARM Holdings is a company, and they don't make any chips. They only sell the IP. That is, they create the architecture, and it's given to the semiconductor giants who produce chips around it, and they earn out of the royalty. So that's how the ARM holdings work, and they use, I mean, they have their own different kinds of microcontrollers that they have produced for different kinds of activities. Basically, there are three profiles. One is the M profile, one is the A profile, and one is the R profile. The A profile microcontrollers or processors, as you can say, are actually being used uh, in in mobile phones, basically, and they have a decent amount of RAM and decent amount of clock speed, and they have decent amount of flash memory as well. But they are not as powerful as, what you can have on a desktop or a laptop. But yes, they are good enough. And then we have the real-time grade, which is used in real-time embedded systems where the response times from the application is of paramount importance, like critical industries when it comes to aerospace or automotive. For example, if it is being used for anti-brake lock system, the ABS should employ within a few milliseconds so as to avoid a crash. And and the microcontroller grade, that is the M grade, is generally used for a normal embedded tasks, like we have different devices for example, we have a washing machine or a microwave, or for that matter a remote control unit, or air conditioners, white goods kind of things, and places where critical behavior is really not essential. So it's basically used in those domains. So basically three profiles: A profile, M profile, and R profile. And TinyML is actually, as I said, tiny machine learning, works on all such devices. Now, you must have, during your entire FDP, you must have seen that machine learning requires huge computing powers. And most of the activity you must have done using Google Colab. And there you must have used the GPUs or the TPUs from Google to actually run your models. Now, that kind of computing power is not even available on our laptops or desktops. Forget these tiny devices. They are actually very, very small when it comes to their memory model or their power requirements. So TinyML is basically, it's going to work on such devices, and specifically whose power budget is less than 1 millivolt. Now that might just, you might just start wondering, like, less than 1 millivolt means we are actually talking about handheld devices or even devices, forget rechargeable batteries, devices that could be running using coin cells. So that is the basic focus of TinyML. So with that in perspective, let's understand for people who are from, I believe there are people from diverse backgrounds in this FDP. So I'll just give you an overview of what all these things are. Like, what is an embedded system in first place? An embedded system is a computing device that usually is small or tiny, like the one that I was holding in my hand, and it operates with extremely low power. So basically, these chips are actually going to run at around 3.3 volts or even lesser than that, because they have to run on battery. And batteries could be rechargeable batteries, or as I said, the coin cell, the one that we find on the motherboard of a computer, which is actually powering up the BIOS, the ROM. So these devices might work on slightly larger batteries as well as like the way we have it in our mobile phones. They have larger batteries which are rechargeable. So TinyML can work on that as well. And basically, TinyML is being employed on such devices rather than actually running such kind of applications on a laptop or a desktop, or for that matter, even on GPUs or TPUs of Google. So what we are talking about is handheld devices. That is our focus. So now, what are the basic constraints that we can have when we talk about such devices? Like embedded systems are resource constrained. Now, what do we mean by that? Embedded systems are resource constrained. The first thing is they have a few kilobytes of RAM and a similar amount of flash memory. So basically, flash memory is a reprogrammable memory. We store our program over there, and the size of the program also matters. There, even a few bytes of, say, even if you could save around 20 or 30 bytes of memory, it's a big saving when it comes to such small devices. And when you start comparing this with the machine learning that you have been doing in the past few days, you must have realized that the computing requirements are extremely high. So this is going to be a big bottleneck when it comes to actually running these models on such devices. Now, this board that I have, it's quite generous. It has around 512 KB of RAM. So that's quite a good size of RAM that I have. But trust me, it can these things can even work at lower RAMs where you have a very small little model doing some specific task. Now, when it comes to embedded systems, they are basically the target is a specific task. So these things are certainly going to work because they are not going to be versatile systems like our desktops or laptops. We actually create an embedded system for a particular task to be run, or a few tasks, like around, say, 4 or 5 things that it might be doing. So the first bottleneck, as I said, when it comes to an embedded system is the memory. And you have seen what memory requirements these ML models have when you have run some code on Google Colab. Then the next bottleneck is the clock speed. Now, these devices that we are talking about, they run on a clock of few tens of few hundreds of megahertz. Like today, what we are going to do is we are going to run a clock for this board at 16 megahertz. Now, compare and contrast this with respect to the TPUs or the GPUs that are made available by Google to us. They are actually extremely fast devices. Or for that matter, if you are doing some machine learning task on your desktop or laptop, it is always advisable to have at least about 16 GB of RAM and about 4 GB to 8 GB video card, because all this processing, this heavy lifting of machine learning processes is picked up by the graphics card. So those are the GPUs, and generally NVIDIA. You must be knowing or heard the name of the company. They lead the GPU market. And even a 4 GB GPU card would cost you around 4,000 rupees to 5,000 rupees. And GPU cards that are required for extremely complex machine learning tasks may run into lakhs. So that is how it is. So we are actually saying that we are going to run some decent machine learning models with a few hundreds of megahertz of clock. And or most of you might be aware of this. As we go on increasing the clock speed, the energy requirements also increase. That is, I cannot run a handheld device that is battery powered at extremely high clock speeds because that's going to drain off the battery. And the more it drains off, you need to constantly recharge it. So you need to actually have the clock under control. Now, when it comes to machine learning, the speed is critical. So if it's not having that power or that clock speed, your machine learning models might not even run. So that is the second bottleneck. I can't run these devices at extremely high clock speeds because that's going to drain off the battery. That's the second bottleneck. The third bottleneck is we have 64-bit processors or these GPUs, or maybe even having a higher bitage. But we have these devices that are either 8-bit to 32-bit processors. We are in that range. We are not in the 64-bit processor range. So these are 32-bit or 8-bit processors like 8051, and trust me, 8051, all those who are from the embedded background might just write off 8051, but 8051 is a strong product manufactured by all the manufacturers of silicon. That is all the big giants, the semiconductor giants actually manufacture an 8051, and it has got numerous new features that are being put into that chip. So 8051 is still there and very much there. It's the most elegant architecture to have. And the most popular one is the ARM Cortex, which is 32-bit. So these are the markets that, and you have 16-bit processors also in between. But the focus is either on an 8-bit just to save power or a 32-bit to have that extra crunch when it comes to processing. But when it comes to machine learning, the full-fledged machine learning, these processors are nowhere. I mean, they just will die. They cannot handle this processing power. I mean, this processing that is needed. Then the next is we don't have any kind of an operating system that is running on these. So that's the next bottleneck. So basically, we've seen three bottlenecks: the memory, the clock speed, the bitage of the processors, and then comes the OS. There is no OS. They are bare metal. Or they might have some kind of a small little scheduler kind of a thing like the Micrium or the Embed or the Keel RTX, to name a few. Or you might create your own scheduler to actually schedule tasks on these devices. So all the necessary mandatory requirements when somebody talks about machine learning, none of them are actually being satisfied by an embedded system when it comes to machine learning. So then you might just start wondering, oh, nothing is, I mean, when we say system requirements, none of the system requirements are matched. Then how is this going to work? And how much amount of work we would need to do to make this work? Trust me, it's not that difficult. Google has made life easier. And it's like I'm not an advocate of Google, neither do I work for Google. But yes, they have done some amazing research and they have made these things possible because this is the future. And Google is investing in the future. And they know, I mean, they will get the returns out of it. So, what is the future now? Let's see. So, why TinyML? Why do we need this? Why TinyML? So we understood what TinyML is all about. It's tiny machine learning on small devices, hence called tiny. Machine learning on small devices. So that's the reason we call it as tiny. So Why this? If you look around, you will see that tiny machine learning has penetrated our lives already. The first example that I can give you is, OK Google on your mobile phone. You just say OK Google and it wakes up. You have natural language processing at work over there. And the phone understands what we are saying. So what is happening over there? You are using some kind of machine learning on the phone. Now, you know how your phone is. I mean, it's not an extremely powerful device. I'm not talking about those extremely expensive mobile phones. Even a small little mobile phone that is an Android powered device that may cost you around 5,000 to 6,000 rupees. Okay, Google works on that, as well as it works on 1.25 lakh iPhone. So basically, it's running on the smallest device that is available for Android phone. When I use the word device, most of the times it will mean a chip or a microcontroller or microprocessor. So as I said, OK Google is going to work on all these phones, no matter how costly or how cheap the phone is. So if the phone is cheap, naturally the hardware that has gone into it, the amount of RAM, the amount of ROM, the kind of processor that has gone into it are all lower end kind of devices. But it works over there. Another example that I can give you is we just give a thumbs up or a thumbs down on social media. And this data is used by the systems to show us information that we want to see more. Like when we read some kind of a particular news on your mobile phone, we get feeds related to that news. Some people might follow the stock market, some might follow the technology. So you might just see that the news articles that you generally get into your recommendations are very closely related. What's happening over there? Machine learning is at work. Next, I can give you one very good example when it comes to your mobile phone. You must have used Google Lens on your mobile phone. You hold your mobile's camera in front of an object, or say some kind of an unidentified insect comes into your house, and your kids are very curious to know what that insect is, and they ask you what it is. Even you have not seen that insect in your lifetime. What do? You hold your mobile camera and turn on Google Lens, and within a few seconds, it gives you recommendations, 4 or 5 recommendations about the name of that insect. So what is happening over here? Machine learning is at work, and it's basically some kind of image classification that is happening through the mobile phone's camera. Where is this all happening? Of course, today it's most of it is happening in the cloud in the data centers of Google. But you must have seen that all these things require internet. We'll come to that. I'm just giving you some use cases. I mean, it's already there. Then there is, we have these autonomous cars. Their segmentation is being used. Segmentation when it comes to machine learning. And what is this that we are talking about? What kind of segmentation? The segmentation would be like the car identifies whether there is a human on the road so that it has to stop. It's an autonomous car. Which are the lanes on the road? How are the lanes classified? Of course, in India, we don't have the classification for the lanes, but in the West, they are. And already these cars are right over there. Where are the shoulders of the road? Shoulders meaning at the edge of the road, we have the footpath. So it identifies the shoulders. So the class segmentation is done that way. It's segmenting the humans, it's segmenting the lanes, it's segmenting the shoulders of the road. So basically, segmentation is at use, and it uses colorizing or pixelizing techniques for that entire image into different categories. And most importantly, when it comes to autonomous cars, it's not possible to do machine learning in the data centers. It has to be done right inside the car. I'll come to that very important aspect. So And it has to be instantaneous. It's not that it should take some time, say around 4-5 minutes before it identifies the human. By that time, the human might be under the car, crushed to death. It has to be extremely, extremely fast. And you cannot have a GPU running inside a extremely powerful GPU or a TPU running inside your car. What would be the cost of the car? Nobody is going to buy that car for that cost. So all this is already there. It's just that now it's penetrating some other spheres of our life. Another example that you can see on your screen is smart glasses. What are these smart glasses? Smart glasses might be used for translation purposes. Like you are talking to a person who is speaking Mandarin and you don't understand Mandarin. You are a person who talks Hindi, not even English. And both of you are wearing these glasses. Whatever he's talking in Mandarin is getting translated to Hindi. Why? Because you're wearing these glasses. So this translation has to be instantaneous. It cannot take time. It cannot, I mean, you cannot have that liberty of sending this data to a data center and then processing it over there and getting it back. As the person is speaking, the translation should happen in your ears. So this is where such things can play a very vital role. So from what we have seen, all these examples that I've spoken about, this requires a lot of data and lot of data processing. And you must have learned during your entire journey of this FDP that the more the data, the better it is. Now, if I say I need a lot of data, my embedded system cannot support that kind of data because its memory is small. It cannot do that kind of processing because its clock speed is low. It's not that powerful when it comes to the bitage. So summing it all up, the requirements of ML are at the other end of the spectrum. And the requirement of an embedded system is at the other end of the spectrum. So there is a wide gap in between. Machine learning requires remarkable amount of computing power. Data centers are actually used to provide these computing capabilities. Whenever we do some machine learning, we are going to connect to some data center of Google or Amazon, AWS, or Microsoft. And all this machine learning takes place over there in their data centers. But what do they do? When we say we connect to their data centers, what is actually happening over there? In their data centers, let's talk about Google. To provide such computing capabilities, this extremely heavy requirement computing capabilities, companies like Google use tensor processing units, TPUs. You must have seen that you change the when you are in Google Colab, you can change the environment. It's by default it's none. The second option is the GPU, and the third option is a TPU. So if you are going to use GPU, if the model is extremely big or you want things to be pretty fast, you can switch over to the GPU and make your model run on the GPU. But if your requirements are even more, you can make it run on the TPU, the tensor processing unit. Now, what is a tensor processing unit? You must have heard about it, or you must have learned during the FDP. Tensor processing unit is a application specific IC. It's an ASIC, which is developed by Google, and they are optimized to work with tensors. And machine learning is all about tensors. So companies have put all this hardware already in place, and the data centers are providing that kind of computing capability. So things are pretty fine, and they are extremely good. So these ML applications run extremely, extremely fast because you are using their hardware and it's free of cost. But remember, all these data centers are located at fixed, limited places. So comes the biggest hindrance. What is that? This limits the interactivity of your applications. You cannot have instantaneous outputs. For example, if you take a picture on your mobile phone and you want that the system responds to a particular action in the picture instantaneously, I'm talking about some kind of gesture recognition. Is it possible that you get an instantaneous reply? It's not possible. One, for varied reasons. One, because first is you're sending the data to that data center. You capture the image on your mobile phone. The data is uploaded using your internet connection. It goes to the data center. At the data center, the processing happens pretty quickly. And because, say, you're using a TPU over there, and the results are then sent back to the internet, and back they come to your device. So now the data has to go from your device to the data center, from the data center back to your device. What happens? This introduces latency. So this interactivity that you need in your pocket is lost. So one big bottleneck that we have still, and it will be there for years to come, is all this talk of 4G and 5G data. We cannot guarantee that we will get this good network bandwidth everywhere in all parts of the world. So ultimately, no matter how good application you make or how good your hardware is, it's all limited by this network connectivity. So your interactivity is limited by that. You have no control on this. You cannot say you may get this network 24/7, 365 days in all places of the world. The way you got in Mumbai, the same you'll get in some remote place in Maharashtra. It's not possible. So what's the solution? No matter what kind of company comes up, at least there is no solution to this, because these are radio waves. There are a lot of factors that affect propagation. So this latency is always going to be there. You cannot do anything about it, at least as of now. So what's the way out? I want that interactivity, but I cannot get it because of this latency. If I have to create a host of such applications, which are, we are talking a lot about machine learning and artificial intelligence doing all sorts of things. And people are talking about getting all these applications on the mobile phone or some kind of an embedded device. But all this is going to be ultimately limited by the network's bandwidth, which is not guaranteed, and nobody can guarantee that. So the solution, do all this machine learning processing on this device itself, on your mobile phone or on these small chips. So now it's not just about a phone. We are just focusing on the phone because most of us are using the phone. Common people use the phone. But what about industries? What about applications that may be useful for the future? We have to be able to do machine learning on this device itself. We may have a lot of intelligent devices with many different kinds of sensors in them that are sensing our environment and helping us improve our lives using machine learning. So if ML is done on these devices, there are a host of new applications that can be designed around these devices, because there is a real-time interactivity that we can achieve. Imagine we do all the machine learning on the device itself. The network is totally cut off. We don't need the internet. And we get that interactivity that we want right in our pocket. And that's possible with tiny machine learning. So today, if you see the estimates, and these are true estimates, today IoT devices, that is Internet of Things, they are basically intelligent sensors. IoT devices produce about 5 quintillion bytes of data. That's 10 raised to 18. Now that data is just about 1% of the total data that is being used for machine learning. So 5 quintillion bytes of data is just about 1% of the total data that is used for machine learning. Imagine if we could use the remaining 99% of the produced data for ML, where, I mean, what we can do. That it's just beyond imagination. Now you would say, what kind of devices? I can give you I can say tomorrow even a chappal manufacturer might use machine learning. Now you would ask me, what is the purpose? I mean, what is a chappal manufacturer going to do with machine learning? Create boots or chappals that suit a particular person's gait, posture, and gives him the best feeling or the best, best kind of walk, so that he doesn't have any kind of pain which otherwise a person feels when he puts some kinds of chappals. You must have witnessed these kinds of things. You may have to many a times the doctors tell you may have to change your boots or your chappals just because your legs are paining. Now we use trial and error methods to try out different chappals. You can have some sensor, some device into your chappal sole, and it's actually using sensors to understand your gait, your posture, your walking speed, the angle at which your ankle is falling when it's on the road. And all this data, this is useful data. This data may be processed inside the chip on that chappal itself. And then this data could be used by the chappal manufacturer to actually have a sole that is designed to give you maximum comfort. This is all going to happen. This is data, this is useful data. This data needs to be processed and processed right over there. So when we say we are just looking at about 1% of data, so there is a lot of data which is going unused and which could have useful knowledge, which if used can make, I mean, it can give rise to an altogether different industry. And that is what is happening now. People who have realized this have come up with innovative ideas, and it's just about, pumping in the funds to make this come true. But trust me, it's going to be, you will find a host of different industries come up around these things. If we can use that data, that is still not, that's just going, I mean, it's not used, it's just lying over there. So these small devices are all around us. These are sensors, these are all around us. Hence, it is said widely that tiny is bright. And ML is tiny and bright. That's the saying or the keyword today. So many of these machine learning applications are moving from the cloud to the edge. Now, what is edge? These are nothing but these are devices that are connected to the internet, IoT devices. They are called the edge devices. So because of this latency that is there, all the work that was being done on the cloud, people have realized that it makes sense to make that work on the chip itself rather than sending it to the cloud. So machine learning applications are moving from the cloud to the edge. Now that's the new trend. These small devices are pervasive. That means they are everywhere and can now interact with each other. And a whole set of new applications and industry can be born. That's what is, that's the future. Hence, the future of machine learning is truly tiny and bright. Machine learning is there, but it's all about being tiny. Do machine learning on these devices. The real challenges are in making ML work on such resource constrained low power devices. Now, I have already laid out the basic constraints that we may have with these devices. And what are the requirements of ML? ML requires extremely powerful processing devices and storage for storing huge amounts of data, which embedded devices cannot. If such data is processed on such low power devices, it may drain off the battery. if it's a battery, and most of them would be battery powered devices. So there lies that challenge. We need to overcome that. We need to overcome the challenge of the memory requirements. So what is the way out? Create a small ML model that works on these devices by overcoming all these hindrances. So we create a machine learning model that's going to run on these tiny devices. Hence, it's called TinyML. Now you have learned about machine learning, but I will love to put things in perspective because it's very essential that the workflow is almost similar, but there are a lot of other nuances which you need to really understand when it comes to machine learning. So what is this? In machine learning, we have, I can compare machine learning with classical programming, the normal programs that we write. In classical programming, we have rules and we have data. We write a program with, following a fixed set of rules, and we provide it with data and out come the answers. That's the classical approach of uh, programming. Okay, so that's the classical approach of normal programming. So just to put things in perspective, in classical programming, I'll give you an example. If I have to write a program which actually tells me whether a number is positive or negative, I can have three rules which come to my mind. If the number is greater than 0, it's positive. If the number is less than 0, it's negative. And if it's equal to 0, it's a 0. So these are the rules. And I provide it with data and I get the answers. So all these three rules are known to me. I know these rules. But there are n number of problems in this world in which you cannot know all the rules all the time. Like, for example, if it's an image classification problem and I want to classify animals. So as a programmer, normal programmer, I may think that what would be the rules? An animal, maybe a four-legged animal, it will have a tail, it will have 2 ears, 2 eyes. It might have a snout. That's it. And that will classify it as an animal. But will it allow me to classify that animal as a lion, as a tiger, as a cat, as a monkey, as a donkey? No. So how many rules would you know? You don't know all the rules. So what is the way out? Your program is going to fail if you don't know the rules. So how do you figure that out? So came machine learning, in which you give a known number of answers along with that data, and you make that machine learning model figure out the rules for you. And that is the process that we call as a training, basically. So your machine learning model actually figures out those rules, and then you can give it unknown data and you get your answers to that unknown data. So this is how machine learning works. So as it is said, and you have learned, the more the data, the better it is. So again, that's going to be a big problem for us when it comes to tiny machine learning. And making that model to learn so many rules, if at all it's an image classification example, it's going to be a Herculean task. How much amount of data you may need to feed into your model to actually make it happen. So that's going to be a big Herculean task that you may have in front of you. So as I said, getting the exact combination of factors that predicts a given state is very difficult. So you don't know what are the different cases that may exist, and machine learning is the only way out. For example, say, since we are talking about small devices, let's assume that it's a factory and I have a machine and there are sensors on that machine, and I need to find out, and I have a very busy production line. I cannot stop that machine and say the machine fails. What happens? Your production line is down, and you don't know how much time it's going to get to repair the machine to put it back into the production line. So what is the way out? Use machine learning. Machine learning will help you predict it, predict the failure. Now to do that, what is needed? Data. What kind of data? Say we may find out, we may have a lot of data related to the factory, the production rate, the temperature, the vibration level. These are to name a few, or even some data that may be associated with other factors in the factory. But is all this data going to be affecting the failure of the machine? No. So you as a developer, you have to be looking out for that data first that is going to be really instrumental in the failure of that particular machine. So pick up only that data that is essential. Don't pick up all the data that you feel might be, that's the data that is being produced by the factory. Don't use all that data. Pick up the data that you feel is critical to understanding the failure, like the vibration level, some kind of sounds, the temperature, the amount of production, the rate of production. The production rate may come up, down. Depending on that, you may know that there is something wrong that is happening in the machine. And use that data. So basically, it starts from there. What data is necessary and what data you feel is required to actually understand how and when the machine is going to fail. Picking up the right data is extremely critical. So basically, what are we talking about? So to create that machine learning program, we will feed this data that we have collected related to the machine into a special kind of an algorithm, and that algorithm discovers the rules. This means that we as programmers can create programs that make predictions based on this complex data without having to understand all the complexity of our rules, or complexity ourselves. The machine learning algorithm builds a model of the system based on the data that we provide. And this is the process of training. This is what we call training. So it's building a model based on the data that we have provided. So as I said, select your data correctly. And this model is nothing but a simple computer program. We run that data through this model to make the predictions. This is the process of inference. So these predictions that we would be making is nothing but the process of inference. The machine learning system is trained rather than explicitly programmed. We don't do explicit programming the way we do in traditional programming. And you know why it is so. I told you that. It's presented with many examples. That is, to this model, we give a lot of examples that are relevant to the task, and it finds a statistical structure in these examples that eventually allows the system to come up with rules for automating the task. So if the data that you have provided is relevant data, it will come up with the correct rules to automate the task. And what is the task? To predict failure based on the data that I have given, so that I know that this machine is going to go down in the next few days. I can always have a standby machine ready, which I'll put into the production line as quickly as possible after this fails. So for instance, if you wish to automate the task of tagging, this is another rule of tagging your vacation pictures. You could present a machine learning system with many examples of pictures already tagged by humans. And the system would learn the statistical rules for associating specific pictures to specific tags. Now, what is happening over here is when it comes to that factory machine problem or this pictures tagging problem, all this has to be right over there. You cannot send this data to a data center for a reason. One is security. You cannot have your factory related data out in the public domain, making some processing happening in some data center remotely located, which you don't even know where it exists. That is from the security aspect. So all this has to happen right over there and right at the machine level, or for that matter, the pictures. You may have some very personal vacation pictures which you don't want in the public domain, but nonetheless you want to use the application. Create it for a device or a small device in your hand. Now, when it comes to these, I just gave you some examples of what we can do with these tiny devices. Now, there are different approaches to machine learning, and I believe you have gone through most of them during this FDP training. But I would like to focus on the most popular ML approach, that is deep learning. So, deep learning is based on a simplified idea of how human brains might work. So this is one type of approach of machine learning, which is called deep learning, and it works on a simplified idea of how a human brain works. So in deep learning, a network of simulated neurons represented by arrays of numbers is trained to model the relationships between various inputs and outputs. So basically, neurons are nothing but array representations of numbers, and we are actually training these neurons to figure out the relationships between the inputs and outputs. These are mathematical relationships, basically. So different architectures or arrangements of simulated neurons are useful for different tasks. So what does this mean? Actually, you can have neurons connected in different manners and different ways for different kinds of tasks. So that gives rise to different kinds of architectures. Some of the architectures are extremely good at extracting meaning from image data. That is, many a times it is an image classification problem. And some specific architectures might really work well with such kind of image extracting, meaning extracting models from that image data, while some architectures might be very good for predicting the next value in a sequence. Deep learning is a flexible and powerful tool for solving different types of problems. And most importantly, why deep learning? Because it's well suited for microcontrollers, that is small devices. So we are focusing on deep learning because it's well suited to run on microcontrollers. That's the basic idea. That's the reason why we are, looking at deep learning in first place. So this has been identified as the best way to work with a microcontroller for machine learning. So what is deep learning? Just to give you inputs into what deep learning is. So to do machine learning in general, we need three things. Input data points first, that is your data. Then a way to measure whether the algorithm is doing a good job. And third, a machine learning, transforms its input data into meaningful outputs. A process that is learned from exposure to known examples of inputs and outputs. So basically, when I say input data points, it could be, if the task is speech recognition, the data points could be sound files of people speaking. If the if the task is of image tagging, they could be pictures. So the data points could be pictures. And what could be the outputs? In speech recognition, these could be human-generated transcripts of sound files. In an image task, the expected output could be tags like I have like what Google Lens uses. It tags whether it's a cat, it's a dog, or what. So this is the first requirement. Your input data, that's extremely critical. Correct data and correct selected data. Just don't pick up any data and put it in the machine learning model. You should know as a developer or as a domain expert what data is critical and what is not. Exclude that data right away because we are doing this on small devices. It's unnecessarily going to be excess data which is of no use. So first figure that out. Next, we need a way to measure whether the algorithm is doing a good job. Now, this is a pretty common and straightforward thing because that is the very basis of machine learning. This is necessary in order to determine the distance between the algorithm's current output and its expected output. That is, I am expecting some output and whatever output that I'm getting is not very close to it. So in that case, I will use this output or this measurement as a feedback signal to adjust the way that algorithm works. So this adjustment in step is called learning. So how this is going to be used as a feedback signal, and we are going to use that feedback signal to make the model learn. And the third one, as I said, the machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. Therefore, the central problem in machine learning and deep learning is to meaningfully transform data. That's the key. The central idea is to meaningfully transform the data that you got. In other words, we are actually learning some useful representations of the input data at hand. Representations that get us closer to the expected output. So we are actually, what we say, we are getting some meaningful data that is transformed is nothing but we are getting some useful representations. And these representations will get us close to the output. So that is very critical when it comes to small devices. So these representations have to be extremely close to your desired output because you don't have that liberty to keep running this training on these devices because they are battery powered. So what is this useful representation of data means? It's basically a different way to look at data, to represent or encode data. Now, what does that actually mean? I mean, if I have to give you an example, say, let's assume that we have a color image that is to be encoded in the red, green, blue format, RGB, or HSV format, that is hue, saturation, and value format. These two different representations, these are two different representations of the same data. So now what representation you need to correctly arrive at your required output, that is what is very important. So it's like some of these tasks might be difficult with one representation, but can become easy with another representation. Like doing something with the RGB format might be easier than doing something with the HSV format. So I have to use the RGB format rather than the HSV format for that same data. So that is what I mean by representations. So learning basically in the context of machine learning describes an automatic search process for better representations of this data. So when we talk about learning, we are actually trying to figure out which could be the better representation of the data. And that is what learning is all about when it comes to machine learning context. What is learning? It says the model is learning. So it's actually figuring out which is the better representation of that data so that I can arrive at the output in a, I mean, I can get an output that is meaningful for me. So machine learning means searching for useful representations of some input data within a predefined space of possibilities using the guidance from the feedback signal. That is how far my output is from the reality. Deep learning actually puts an emphasis on learning successive layers of increasingly meaningful representations. That means we have layers of these representations. So the deep in that deep learning is actually the idea of such successive layers of representations. So when we say that we are using a deep learning model, it's the deep means that it is the deep is the idea of these successive layers of representation. So what representation we have used, we are actually distilling, or it's a process of distillation of these layers till we arrive at the output where it is extremely distilled or filtered data which is actually representing something. So the number of layers define the depth of the model. The more the layers, the deeper the model is. In deep learning, these layered representations are learned via models, and these models are called neural networks. They are structured in stacks, or sorry, layers, we would say, that are stacked on top of each other. So they are layers that are coming up one after the other. So deep network is a multi-stage, you can view it as a multi-stage information distillation operation, where information goes through successive filters or layers and comes out increasingly purified. So basically, this is how the data travels through these layers. If many of you must have run different models on image data, you must have seen what are the how the convolutions take place intermittently, and how that image is broken up so that the features are highlighted. So basically what you are doing, it's in simple words, put simply, we are distilling the information. It's about distillation. That's the reason you need these layers. So more the layers, the distillation may be high, but that's not always the case that you may get a correct output. Many a times it is a trial and error method, experimentation. So deep learning is summarily a multi-stage way to learn data representations. So I hope you've understood what I'm saying, what I'm talking about data representations. And it's a multi-stage way. That means we have multiple layers of neurons that are actually working at it. So the next thing is we are actually going to see is how this deep learning really works. What are the underpinnings of deep learning? Because that's extremely essential that you understand how it works internally, because we are going to work with small devices. So having a little bit understanding of how it works internally will always allow you to create a model that's going to really work on your small little device. Because you have to keep all that in mind when you're working with TinyML. Because you have constraints. You have to work within those constraints. So how deep learning works? Machine learning is about mapping inputs such as images, for example, to targets such as a label. That is, for example, a cat, dog, monkey, lion, whatever is the label for that image. So which is done by observing many examples of inputs and targets. So basically you're feeding a lot of inputs and the labels, and you're training your model. You also know that the deep neural network do this input to target mapping via a deep sequence of simple transformations, that is layers we talked about. And as these transformations are learned to by exposure to examples, that means you're giving it a lot of examples, and all these transformations are learned by that deep learning network using these examples. And how does it do it? It's a very simple flow chart. You can understand what is the goal. We find out the right values for the weights that we are going to apply to that layer. We have an input for the input layer. From the input layer, it goes to there is just one output layer over there. And we are going to apply some kind of weights on the input layers, the hidden layers, and we are going to get some predictions. So I gave some input, I applied some weights, and I had the layer, and I got some predictions. Now, what are these predictions? The specification of what a layer does to its input data is always stored in the layer's weights. It's known to you. Weights are nothing but a bunch of numbers. Everything is numbers over here. And many a times they are floating numbers, floating points. Learning means finding a set of values for the weights of all the layers in a network such that the network will correctly map example inputs to their associated targets. So you apply some weights so that it will, whatever inputs you give, the layer will map it to your associated targets. Now, how closely that mapping is done, that tells you how good the model is. So to begin with,
or
the weights have a random value. Hello? To begin with, weights have, did somebody say something? Okay. To begin with, the weights have a random value. This produces some output. When we start, we give it a random value. The weights are random. We don't know what inputs, what weights we have to use. So this will produce some kind of an output. To control the output of a neural network, you need to be able to measure how far this output is from what you expected. So that is what is very essential. That means you got the prediction. Now this prediction, how far it is from your expected output, you need to see that. Now, who's doing that? It's being done by the loss function. It's known. We know it. So the loss function takes the predictions of the network and the true target, that is the target value, what we want, and computes a distance score. That is how far it is away from the expected output, capturing how well the network has done. That means it tells us how well the network has worked to give us that prediction. That is the job of the loss function. So now we have introduced the loss function into our design, and this loss function is calculating how far it is away from the actual truth. That is what we have done. Further, now once that is done, we have to actually have a further thing called as an optimizer. What does it do? The distance score is used as the feedback signal to adjust the value of the weights a little in the direction that will lower the loss score. That means now whatever loss we have got, we are actually using the optimizer to actually feed that. It's actually working like the feedback signal, and now it's being fed back and the weights are being adjusted so that the loss function goes down and down. And this is actually the feedback signal, and it uses a algorithm called as the backpropagation algorithm. So initially the weights of the network that we have used are random. We have just thought of some weights and we have applied. So the network merely implements a series of random transformations. That means it starts working and some transformations on that data start happening. So naturally, since it's random, its output is 100% going to be far from what it should ideally be. And the loss score is 100% going to be very high. But with every example that the network processes, the weights are adjusted a little in the correct direction. And the loss score goes on decreasing. This is what we call the training loop or the epochs, which is repeated a sufficient number of times, typically tens of iterations over thousands of examples, that yields the weight values that minimize the loss function. A network with minimal loss is the one which outputs are as close as they can be to the targets, and that is what we call a train network. So basically, we are when we say we are going through the epochs, we are using the training loops, and all this data that we have during the training is being passed, and the weights get adjusted to the correct direction to minimize the loss score. And the lower the loss score, the better is your network. And that is what we're talking about, the training data. So now, what is the basic flow or the workflow of a deep learning network? So basically, the deep learning workflow is first decide on the goal, collect the data set, design a model architecture, then train the model, convert the model, run the inference, evaluate, and troubleshoot. Now, when I say this is the common deep learning workflow, everybody knows about it. Now, when we come to our small, tiny devices, as I said, you should your goal should be very much, focused. You should exactly know what you want to do, because embedded systems are goal oriented. They are not multi-purpose, or they are not versatile like our computers or our desktops. They are designed to do a specific job. So over here, your decision of your goal should be bang on. What you want to do? You need to decide what you want to predict, so you can decide what data to collect and which model architecture to use. You are not at liberty over there to have some kind of model that's extravagant on memory, but still it's working. That's fine when it's on extremely powerful devices, but here you don't have the liberty. So you have to be very, very categorical when you are selecting your data or your goal. So let's assume we have this factory machine example that we spoke about earlier. My factory machine is going to break down. It's going to break. So I want to be able to decide whether the machine working is normal or abnormal. So I have boiled it down to a problem of classification type. So I have just two classes. One is normal operation, one is abnormal operation. Meaning, abnormal operation meaning that the machine is showing signs that it's going to break down soon. This means that my goal is to create a model that classifies our input data as either normal or abnormal. This is very, very important. If you falter over here, trust me, you will have to go through a numerous iterations when you are actually going to port this to your microcontroller. Because your model might work on the computer, on Colab, but when you port it, you realize, oh, my chip is not supporting the memory. I mean, I don't have that much memory. I don't have that much computing power. And you cannot change those parameters at that stage, because other development of that particular, say, a piece of hardware is already over. And now you are training a model. You can't do that. You can't change your specifications later. So you know the limitations of your device. Based on that, you have to fix up your goal. That's very, very important. Next, because many a times it has been observed that the full focus is on designing a great architecture, training the model. But when it comes to deciding on what exactly you want out of it and what kind of data you need to collect, people falter over there. They use all sorts of data that is available with them, just under the impression that it's going to only help in predicting, in giving good predictions, but that's not the case. In a machine failure model, which I'm going to say design, I need not have the data for how the cafeteria's temperature is there on particular days. Because that machine is not located in the cafeteria, it's located in some other place. So select relevant data. So collect a data set. A factory is likely to have a lot of available data, as I said, ranging from the operating temperature of the machine to the type of food that is served in the cafeteria, or even for that matter, the sound or the temperature that keeps fluctuating in an adjacent room. That's not going to affect it. So just leave out that data, irrelevant data. Because when it comes to machine learning, the big misconception is, I mean, you need a lot of data, but the misconception is people pick up any data just to put that data because it's big data. So don't do that. Be very selective about the data, as I said. Do not use irrelevant data, since it's unlikely that, as I said, the cafeteria food has an impact on the functioning of your machine. We can probably exclude that out of the data set. You should always try to combine your domain expertise with experimentation when deciding whether to include some data or no. As an expert of some particular, say you are a mechanical engineer, you can always talk to the mechanical engineer or an electrical engineer on the different parameters of that machine and what impacts its failure. What are the factors that impact its failure? And you can also use statistical techniques to try to identify which data is significant, because all this data is generally logged. So if you're still unsure about including a certain data source, you can always train two models. Train 2 or 3 models and see which one works the best. Experimentation is the key in machine learning. I am a strong believer of that. You cannot have, because most of it is, stochastic kind of information. So experimentation is the best way to go forward if you have to design an extremely good machine learning model. Suppose that we have identified our most promising data as a rate of production, temperature, and vibration. These are my 3 most important vital parameters. I've identified it. And understand one thing over here. These 3 data points, that is production, rate of production, temperature, and vibration, it is time series data. So I know now this is a time series data. So I need to actually understand, if I have to capture the correct data points, all these 3 should be there. So our next step in this is to collect data so that we can train the model. So now what is this data collection? It is difficult to know exactly how much data is required to train an effective model. Nobody knows that. Nobody can claim that you should have this much data. There is no, science behind it. It depends on a multitude of factors, and these factors are different for different problems, such as the complexity of the relationships between different variables. What is the relationship? One variable might be dependent on 2 other. Those 2 might be dependent on 4 other variables. The amount of noise in the system, the data could be noisy, unwanted things would be there in that data. The ease with which classes can be distinguished. How you can classify them into classes. But nonetheless, always remember, one thing is true, and it's scientific. The more the data, the better. The more does not mean more in the sense all kinds of data. The more means a lot of data that is very specific. Like, as I said, we have identified rate of production, temperature, and vibration. I have a lot of data points for this particular data to work with. Next, we have to make a model. So we have collected the data set. Next, we make a model. So there are many types of deep learning model architectures designed to solve a wide range of problems. When training a model, you can choose to design your own architecture, or you can base it on an existing architecture which is developed by researchers. And for many common problems, you can get some pre-trained models freely available on the internet. So you have to identify whether you want to create your own model or use some pre-trained model. When deciding on an architecture, you need to think about the type of problem you're trying to solve, the type of data you have access to, and the ways you can transform that data before feeding it into the model. So we have seen data transformations are very essential. You should know what transformation is needed and what kind of problem you are trying to solve and what data you have. Data which you don't have or it's going to take some time, you cannot include that data. So whatever data you have, try to figure out if there are any relationships. Because we are working with small models, you have to be very, very selective about this. You also need to think about the constraints of the device. This is very, very important. Ultimately, it's boiling down to the constraints of that device on which you are going to run this model. Since they are microcontrollers, they have limited memory and slow processors. So you have to be extremely selective about what you're doing. We might start training a simple model with few layers of neurons. You must have done that previously. And then refine the architecture in an iterative process until we get a useful result. That means see whether removing a particular layer, what effects it has, how small the model becomes, or whether the number of layers are insufficient to correctly represent the problem at hand, whether you want to add some more layers. This is an iterative process and you need to do it. It's not going to be you do it once and you know you have got it. No, the lesser, see, a particular problem may be solved using 4 layers of neural network or just 2 layers. Even 2 layers is giving you that same kind of accuracy, which is somewhat closer to the 4 layer, and you're happy with it, and it's not going to affect your final outcomes. Go with a 2 layer model because that's going to reduce the processing requirements of your chip and ultimately save you power if it's going to be a battery powered device. This is very, very important that you have to remember. So just because you're getting, and the trade-off is always, how much accuracy you need, that you have to decide. So if you are okay with a little bit of variation in the accuracy, always go in for a model that is smaller and less complex, because that's ultimately going to affect the processing that's going to happen on your microcontroller, and it's going to save you power, which is very critical in today's world. So we might start by training a simple model with a few layers, as I said, of neurons, and then refine the architecture in an iterative process. This is very, very important. Please follow this fundamental rule. Deep learning models accept input and generate an output in the form of tensors. So basically, we are working with tensors over here. And what is a tensor? It is essentially a list that can contain either numbers or other tensors. One tensor can contain another tensor. You can think of it similar to an array that we have. Generally, we use it in normal programming. You can view it as an array. So deep learning models, which when we are talking about the tensor and the structure of that tensor, which is called the shape of the tensor. And these are some examples of a tensor just to put things in perspective. So tensors can have multiple dimensions. And what does this mean? A vector of shape 4, comma is actually having 4 values in a single dimension. For example, 4, 2, 5, 6 is a vector of shape 4 because it's just in one single dimension. A matrix is a 2D tensor. A matrix of shape 3, 3 has 3 vectors of 3 values each. So you can see there are 3 vectors. The first vector is 1, 2, 3. The second is 4, 5, 6. Third is 7, 8, 9. And each vector has got 3 values. So it's a 3 by 3 shape 2D tensor, which is nothing but a matrix. A shape of dimension greater than 2 is generally called a tensor. That is the technical definition. So anything that is having a dimension that is greater than 2 is called a tensor. So a 2 comma 2 comma 3 means a tensor represented like the one shown below. It has two matrices of shape 2 comma 3. So there are two matrices. You can see the matrices are enclosed in the red brackets. So there are two of them, and each one of them has got 2 rows and 3 columns. So the shape is 2 comma 3 of those two matrices, and the total shape is of that tensor is 2 comma 2 comma 3. And scalar is a single value. It's a zero dimension tensor. Now this is important to understand because ultimately all this is going to be stored as a tensor in our microcontroller's memory. So you should be very much familiar with this notation so that you can play with it when you actually port it to the microcontroller. If you want to. I mean, if there are some issues that come up and troubleshooting, this plays a very vital role. You should be able to quickly visualize what's happening with these tensors. Then what is important is when we are talking about, we were looking at this, we have to generate features from the data. So first of all, what is this feature? In machine learning, the term feature refers to a particular type of information on which the model is being trained. It is nothing but a particular type of information that we are actually trying to train the model. When we were talking about our machine problem, that is factory machine, we had time series data of rate of production, temperature, and vibration when we started off. In the raw form, as time series with different intervals, this data will not be suitable to pass into the model because for a simple reason, you just cannot take this data and just pass it into the model. For a simple reason, we collected the data like this. The rate of production was collected every 2 minutes. The temperature was collected every 1 minute, and the vibration data was collected every 10 seconds. So see, we are going to have a lot of vibration data in that 2-minute interval or 1-minute interval. And in that, say, in 10-second interval, we are not going to have any data of rate of production or temperature. So if I just take this data as it is and I pass it through the model, it's not going to work because it's going to leave out vital information in that 1 minute and 2 minutes interval because that data comes every 1 minute or 2 minutes. So to overcome this problem, we have to select a window of the time, say every 1 minute. Every 1 minute, we are going to capture the data. And what do? Then we find the average of each data over that window. That means take the average of the entire 10-second over that 1 minute window and the average over the of 1 minute of that particular data point and work on averages. And then we label that data as abnormal operation or normal operation of the machine. So we need to generate this or work on this before we actually pass the data just like that into the model. That is the rate of production every 2 minutes, temperature every 1 minute, and vibration every 10 seconds. You just cannot pass this data as it is. Create a window, find the averages of that data over that window, and then use that data. I'll label that data first, whether that particular window is an abnormal, signifies abnormal operation or normal operation, and then pass that into your model. This data, leaving the label, that means we are not counting the label is aside. Leaving the label, whatever data you have now is nothing but the features of that model. So we can then pass this data into our model as a vector, like something like this, the vector that we have 4, 2, 5, 6. So we can then pass this as a vector into our model. with one element for each time series. Okay. So we have, we know the time series, and for every time series, we are going to create a vector. The next step is normalize this data. Generally, the data that you feed into a neural network will be in the form of tensors filled with floating point values or floats. A float is a data type used to represent numbers that have decimal points. We know that. For the training algorithm to work effectively, these floating point values need to be similar in range to one another. So this is very important. You have to normalize your data so that they are similar. You cannot have one as 100 and one as 0.1. So normalization of data is extremely important. Normalize your data. So once you do that, that is, you have normalized your data, you have generated features from your data, you have actually made a model that actually sums up model creation or model design. So we have created our model architecture. The next stage is training the model. So what is this? Training is the process by which a model learns to produce the correct output for a given set of inputs. It involves feeding training data through a model and making small adjustments to it until it makes the most accurate predictions possible. We saw that in that flow chart over there. So a model is a network of simulated neurons. And what are they? What are these neurons? They are nothing but mathematically, they are represented by arrays of numbers arranged in layers. These numbers are known as weights and biases, or are collectively called as the network's parameters. So when this data is fed into the network, it is transformed by successive mathematical operations that involve the weights and biases in each layer. The output of the model is the result of running the input through these operations. And as I said, we start off with random values to begin with for the weights. And the biases typically start with a value of 0. So during training, batches of data are fed into the model, and the model's output is compared with the desired output, which in our case is the label abnormal or normal operation of the machine. That means we have classified it as normal operation of the machine or abnormal operation of the machine. And an algorithm called as backpropagation adjusts the weights and biases incrementally so that over time the output of the model gets closer to matching desired values. And we know training is measured in epochs, that is iterations, and it continues till we decide to stop. That means again over here experimentation plays a key role. How many times you want to run this, I mean the number of iterations, it's more of experimentation. Where you want to stop, at what accuracy. You can control the number of iterations that you run through. So basically how that network looks like is, this is what we are talking about. This is a simple two-layer neural network. We can actually stop the training the model when the model performance stops improving. That is how it is generally. But if you feel that you are happy with, say, around 80% accuracy of your model, you can always stop it. You don't need to train it till it reaches its final goal. It depends on the requirements. When you want to, how much accuracy you want. So we say that when the model has started making some accurate predictions as per your requirements, you say that the model has set to, you say that the model has converged. This can be assessed by seeing the graphs of the model's performance during training. And probably you must have seen it during your entire FDP. So two common performance metrics that we generally use are loss and accuracy. The loss metric, what is loss? It gives us the numerical estimate of how far the model is from producing the expected answers, and the accuracy metric tells us the percentage of the time that it chooses the correct prediction. So basically, loss metrics is like a numerical value. It's a scalar which tells us how far we are away from what we want. And accuracy tells us the number of times that it has given you the correct prediction, in simple words. So a perfect model would have a loss of 0.0. That's ideal, not possible. And accuracy of 100%, again ideal, not possible. Real models are rarely that close, but you can try to come closer, or it is actually the requirement of the problem at hand. I would rather say that. Not everything has to be 90% accurate. It depends upon what problem you are trying to solve using machine learning. So as the accuracy improves, the loss decreases. That's natural. The model's performance can be improved. Now, this is a very critical thing when it comes to our small devices. You can improve the performance of the model by changing the model architecture. You can see how the model is performing, say with 2 layers, with single layer, with 3 layers. And if you feel that there is not much that is happening, go with the minimal number of layers. That will save you a lot of power when it comes to computing. The power means battery power, if it's a handheld device. We can adjust various values used to set up the model and moderate the training process. That is, I'm talking about the hyperparameters. They include, what are hyperparameters? They are basically, they include variables such as the number of training epochs to run, the number of neurons in each layer. So these are the hyperparameters. So I can adjust that. I can change the model architecture and try to create a smaller model which is accurate enough for your work at hand. Just because a model is performed very well with 4 layers and a number of neurons, that you should not be just happy with that. Try to optimize it and try to get it as low as possible. Because you have still not, we are not running this model on the board as yet. We are doing all this in Google Colab. So there, everything is happy. I mean, everything is goody. But when it comes to small device, when you start porting it, you will realize, oh, this looks to be a very big model for this. So then you have to again go back. So right over here, ensure that once you know your desired accuracy is reached, try to see whether you can cut down on the number of layers, whether you can cut down on the number of neurons, and whether at lower number of neurons, lower number of layers, you can make this work. That will make your life simpler when you're putting it up on the device. And that is how generally I do it. A model is not 100% accurate, never it will be, but it is always useful. A model may fail. Now, this is an important thing, and I'm pretty sure you know it. A model fails because of 2 reasons. And what are they? Underfitting and overfitting. So a neural network learns to fit its behavior to the patterns it recognizes in data. So basically, it recognizes the patterns in the data, and the neural network fits its behavior to those patterns. So when a model is underfit, it means that it has not learned a strong enough representation of these patterns to be able to make good predictions. And this happens generally because the architecture is too small to capture the complexity of the system it is supposed to model, or that it has not been trained on enough data. So 2 reasons, as I said, the more the data, it's always better. Train it with the maximum amount of data that you have. And the architecture is very small. That is, the number of neurons are less, or the number of layers are less. So it is underfitting. It's not correctly giving you the predictions. And the other problem, now this is like walking on a tight rope. The other problem is overfitting. It means that it has learned its training data extremely well. The model is able to exactly predict the minutiae of its training data, but it is not able to generalize its learning to data it has not previously seen. That means it's not able to generally apply the rules to unseen data, because it has learned its training data so well that you have got an accuracy of say around 0.98. Often this happens because the model has managed to entirely memorize. It has memorized that training data. That is how it works. It's all in the memory. Or it has learned to rely on a shortcut that may be present in the training data, but not in the real world. Because the data is so correlated that it knows that if this is like this, it would be like that. So that is, it has learned that shortcut during your training process. So that's very critical when it comes to small devices. You may feel that you are training your model, and with very little number of neurons and little layers, you know that it's working extremely fine, and you're happy. Oh, I've created a model that runs with little memory requirements. But it may so happen that your model has learned the shortcut, and it will always be happy and give you great predictions when it works with that data. But when you put it in real world, it's an absolute disaster. So for example, imagine your training model to classify photos as containing either dogs or cats. If all the dog photos in your training data are taken outdoors and all the cat photos are taken indoors, I'm telling you how this can impact. Say I have a machine learning model of cats and dogs, which identifies photos of cats and dogs. And assume that all the dog photos in your training data are taken outdoors, and all the cat photos are taken indoors. Your model may learn to cheat and use the presence of the sky in those photos to predict which animal it is. So this means that it might misclassify future dog selfies if they happen to be taken indoors. So it will classify the dog as a cat because it is not seeing that sky. The sky is absent in that indoor photograph. So this is the shortcut it learned, and because of that, this has happened. So there are many ways to fight this overfitting. One possibility is to reduce the size of the model. That means cut down on the number of layers, the neurons, so it does not have enough capacity to learn an exact representation of its training set. You can use another technique called as regularization during the training to reduce the degree of overfitting. To make the most of the limited data, a technique called as data augmentation can be used to generate new artificial data points by slicing and dicing the existing data. You can mix and match and use your existing data to generate artificial data points. So the best way to beat overfitting when possible is to get your hands on a larger and more varied data. More data always helps. That is the mantra. So have as much data as you have and put it in. Regularization techniques are used to make deep learning models less likely to overfit their training data. They generally involve constraining the model in some way in order to prevent it from perfectly memorizing the data that is fed during training. So basically, it prevents the model to actually memorize what it has learned during training. So basically, when I said regularization, it's actually, we have two types. One is L1 and L2 regularization, which involves tweaking the algorithms used during training to penalize complex models that are prone to overfitting. And another method known as dropout, which involves cutting the connections between neurons during the training. So data augmentation is actually a way to artificially expand the size of training data sets. So this is how you can fight these problems that you may have, and it's extremely essential that you do it the right way when you're working with small devices. And all this is done on the computer first, and then we finally convert it to a model that's going to run on the small devices. So this is done by creating, how we are actually going to fight this underfitting, overfitting. So create multiple versions. One way is create multiple versions of every training input, each transformed in a way that preserves its meaning but varies its exact composition. For example, uh, we can augment our original training data by adding artificial background noise. You can put some background noise and then sifting the samples around. You can move the samples around in the time for speech recognition from audio samples. The performance of the model over training data tells us the part of the story. So how the model is performing on that training data will give you a picture of what to do, because we have put some artificial noise in it. The model has to be tested on validation and test data as well. So this was the training data. So now we go to the validation and test. It is a very common way that we split the data set into three parts: training data, validation data, and test data. And the general or the typical split is 60% of the data that you have should be training, then the remaining 20 for the validation, and the remaining 20 for the test. That is a common methodology that is used by people. And during training, the training data set is used, that is that 60% of the data set is used to train the model. Periodically, what we do is while we are training, we use the validation data set to feed the model, and the loss is calculated. And because the model has not seen this data before, its loss score is more reliable measure of how the model is performing. Now, by comparing this training and validation loss and accuracy, or whichever other metrics that are available over time, you can see whether the model is overfitting. This is a very important thing. You have to be you should have eye for detail whether the model is overfitting or no, because ultimately, when it's going to work on the small device, more optimizations will come in place and things might not work the way you want them to work. So this is an extremely critical task and a critical point of actually seeing your model work. So as the training loss decreases, the validation loss may go up. Because training data, it knows, it has seen, it's trained on that, so the loss is naturally going to come down. But validation data, which has not seen, that loss may go up. This means that the model is becoming better at predicting training data, but is losing its ability to generalize to new data. So what we do, we keep tweaking our model, and training processes to basically improve the performance and avoid overfitting. And we slowly start to see that our validation metrics start to improve. But always remember, there is always going to be a pitfall over here. This process where you see your validation metrics improve also has this unfortunate side effect. You keep on optimizing till your validation loss goes down. So during that process, it may so happen that you are actually pushing the model towards overfitting both the training and validation data. So this is a very tight rope, a tight scenario. You're on the edge. There is a cliff on both the sides. You have to balance this correctly. Otherwise, your model will also now start learning the validation data, which is not a good thing. So you can test that this is not happened by testing the model with the test data. Now put the test data and see how you are happy with your validation and training results. Now put the test data which the model has never seen. And if it performs well on that, you can be sure that it's good enough. But if it falters over there, understand that your model has now learned even your validation data. So after we have a model that performs acceptably well with training, validation, and test, the process is over. The process is over. The next thing that we will see is once you have, see over here, once you have finished training, then comes convert the model. So what are we doing over here? How do we convert the model? To convert the model, we have to focus on TensorFlow. Now, what is TensorFlow? TensorFlow is a free and open source software library for machine learning. You must have used it during your FDP. It can be used across a range of tasks, but has a particular focus on training and inference of deep neural networks. A TensorFlow model is essentially a set of instructions that tell an interpreter how to transform data in order to produce an output. When we want to use our model, we just load it into the memory and execute it using the TensorFlow interpreter. So basically, it's a software library, and it was created by Google, but now it's in the open domain. And Google is investing heavily in TensorFlow development further, and it's an amazing library. I personally like it. TensorFlow's interpreter is designed to run models on powerful desktop computers and servers. You must have used this in Colab. Since we'll be running our models on tiny microcontrollers, we need a different interpreter that's designed for our use case. Actually, the interpreter that TensorFlow uses is optimized to run on extremely powerful computers. We cannot use that same interpreter. We have to use another interpreter that's produced by TensorFlow organization. It's called as the TensorFlow Lite. So TensorFlow provides an interpreter and accompanying tools to run models on small low-power devices. This set of tools is called TensorFlow Lite. That is our focus. Before TensorFlow Lite can run a model, it first must be converted to TensorFlow Lite format and then saved to disk as a file. We do this with a tool called as TensorFlow Lite Converter. This reduces the size of the model and makes it run faster on small devices. So basically, ultimate aim is to make this model as small as possible and make it run faster on a small device with limited clock speed. So the clock speeds are a few hundreds of megahertz. It has to run on that. So that is the work which TensorFlow Lite would really do for us. And that is the reason why we need that TensorFlow Lite. Next is we run the inference. That's the next step. This is the part where our model meets our application code. That means we have created the model, and now it's time that we integrate it with our application code. We need to write some code that takes raw input data from our sensors. As we know, when we are talking about small devices, most of the times these small devices will have some sensors which are going to sense the environment, and this data is used to actually work with our model. And this data is then transformed into some form that our model was actually trained on. We then pass this transformed data into our model and run the inference. This will result in output data containing predictions. That means once it goes through the models, we'll get some predictions. And in our case, when we were talking about the machine, the factory machine, we had decided that the prediction would be just two classes. One is a normal and one is an abnormal. So for models that classify data, typically the scores for all the classes will sum to 1, and the class with the highest score will be the prediction. So here we are going to get some kind of a prediction value, and the highest score of that prediction will be the class. That means if say it says that abnormal is 0.98% and normal is 0.1%. So that means you know that the machine is going to malfunction. So after we have a score for each class, it is up to our application code to decide what to do. So once we know whether the prediction is abnormal or normal, then comes our application code. It has to decide what it has to do if an abnormal state is predicted, and what it has to do if a normal state is predicted. If an abnormal state is predicted, and if it's for a particular specified time consistently, say for 1 minute, then immediately our code should send a signal to shut down the machine and alert the maintenance team. Or if it's critical that you cannot shut down the machine, you can make application code that alerts the maintenance team to make alternate machine arrangements and put that machine into operation and then remove this machine out of operation. So this is how a lot of money and a lot of time, energy can be saved and a lot of losses can be minimized when it comes to an industry, because your machine learning algorithm has actually predicted a failure of a machine that would happen in, that is certain to happen in some days or some hours. And this is where machine learning is nowadays being used in industry. It could also be used in cars to predict when a maintenance is required by the car, and to some extent it has started happening. If you have driven some of the better cars, it shows you a spanner on its display telling you that take it to the service station. So there is some kind of ML that is happening under the hood in such cases. This is where TinyML is coming up. Next stage is evaluation and troubleshooting. So after we have deployed our model and we have it running on the device, we will start to see whether its real world performance approaches what we had hoped it to. Even though we have already proved that our model makes accurate predictions on its test data, performance on the actual model may be different. And even on the, I mean, you are happy with the performance on the board, on the computer. It may not work the way it is expected to on field, because there are other vital parameters also which you might not have taken into account when you designed this model in first place. So reaching a good real world performance can really make you go back to your drawing board and take some more iterations on your model, your hardware design, and your accompanying software. So it's part and parcel. You have to live with it. You may again go back to the drawing board and again retrain the model with some more data sets. And this is the bottom line. If you run into a model, treat it like any other tech issue. Take a scientific approach to troubleshooting, eliminating the possible factors, and analyze your data to figure out what is going wrong. And if needed, redesign your model. That is always there. When it comes to design of such things on such devices, it's going to be a part and parcel of your daily routine. Because many a times we do it by experimentation. You don't know what data is relevant, what is irrelevant. You have given it your best guess, being a domain expert of a particular domain. But in real world, things might change drastically. So it takes some iterations. Always be prepared for those iterations and keep doing them. For me, machine learning, artificial intelligence is more of experimentation and iterations. So never be let down and feel that, oh, it's not working. It's always that we have left out some critical issues and insights into that data. So that is how basically the deep learning workflow is. So we actually started with our workflow over here. And I think most of it you would be knowing, but it is very important that you look at it from the perspective of a small device and not from the normal machine learning paradigm that you follow during your training processes on Google Colab. So decide the goal, collect the data set, design a model architecture, train the model, convert the model, run inference, evaluate and troubleshoot. So that is your normal deep learning workflow. Now, we have created everything. Next is what? Yeah. So now we are going to see some TinyML using TensorFlow. So what are we planning to do? We are actually going to create a machine learning model, and we'll use Python, TensorFlow, and Google's Colab, which is a cloud-based interactive notebook for experimenting with Python code. We will see the Hello World example of TinyML World. We will be using the STM32F4 Nucleo board for showing the working of a simple neural network on a small STM32F4 microcontroller. So what workflow. I mean, what are we going to, how are we going to proceed with this? What are we going to do exactly? So to create a machine learning, how are we going to proceed? I'm sorry. How are we going to proceed? Obtain a simple data set first, train a deep learning model, evaluate the model's performance, convert the model to run on the device, that is on our microcontroller, write code to perform on device inference, build the code into a binary, that means convert it to some kind of a file that I can use on my microcontroller, and then deploy the binary to the microcontroller. That is, put that code into the microcontroller, fuse it in that. And what are we going to design? I mean, I'm going to show you the entire workflow. It's not necessary that you follow it, because here we need the board. There are some software requirements. So I'm just going to show you a demonstration of this, and what exactly we are getting at the output and from where we started. So our goal is to train a model that can take a value X and predict its sign. Okay. So in real world, if you needed the sign of X, you could just calculate it directly. However, by training a model to approximate the result, we can demonstrate the basics of machine learning. So basically, we are going to create some neural network that's going to do this for us. And the data set that we are going to use is, we are going to create the data set in our application code and use that data set. But this will nonetheless show you the entire workflow of what we are doing when we are saying that we are actually going to make machine learning work on a small device like this microcontroller that I showed you right in the beginning. So we have some sine wave like this for people who are not from the electronics or electrical background. It's just that I've given a representation of the sine wave. You can see the peak is at 90 degrees and 270 degrees, and it's a non-linear wave. So we are going to actually create this and make this work on the board, and we will try to pulse an LED on the board with this wave. Okay, that is what we are going to do. So before I actually go out over there, I am just trying to come up on the screen. Yeah. So I hope people over here have actually got a hang of what we were trying to say. Anybody has anything to say? Are we good to go further? Okay, thanks. I got some message. Fine. So let's start off with our process. But before that, I would just like to, sorry, slide. Okay. Yeah. So we are going to use this STM32F446RE microcontroller, which is an ARM Cortex M4 with a 512 KB flash and 128 KB SRAM. So look at the memory constraints. It's just about 512 KB flash. That's where I'm going to store my program. And RAM is about just 128 KB. And we are running this microcontroller at a 16 megahertz clock frequency. And this board has an onboard debugger, so we are going to use that. And we are going to create our machine learning model using Python, TensorFlow, and Google's Colab, which is a cloud-based interactive notebook. To create the code for this embedded system, we are going to use CubeID from ST Microelectronics, and we'll use the Nucleo board. As I said, it's STM32F446RE, and an amazing little chip with a great functionality, a lot of integration on board. And what are we expecting? As mentioned in the goal, we are approximating a sine wave using ML. This model is made to actually run on the microcontroller. As the sine wave will be produced, we will use this sine wave to create a pulse with modulated output, which will pulse an LED on the board. So that is what we are trying to achieve over here. And what machine learning toolchain are we going to use? We will use Python and Jupyter notebooks. We will use Python since it's easy to learn and works well for many different applications and has tons of libraries for useful tasks involving data and mathematics. Python is great when combined with Jupyter notebooks. Jupyter notebook is a special document format that allows you to mix writing graphics and code that can be run at the click of a button. And Jupyter Notebooks is widely used as a way to describe, explain, explore machine learning code and problems. Jupyter Notebook allows us to display graphs and show our models' accuracy and convergence. And to run the notebook, we use Google Colab. Colab is made by Google and it provides an online environment for running Jupyter Notebooks. It also provides, it's basically free and it can be used to run complex hardware intensive ML models on Google's powerful hardware, that is the TPUs or the GPUs from Google. And TensorFlow is also being used. It is a set of tools for building, training, evaluating, deploying machine learning models. TensorFlow was developed by Google and is now an open source project built and maintained by thousands of contributors across the world. It is very popular and widely used framework for machine learning. Keras is TensorFlow's high-level API that makes it easy to build and train deep learning networks. So some part of Keras is going to come in. And finally, for making this run on our board, we are going to use TensorFlow Lite, which is a set of tools for deploying TensorFlow models to mobile and embedded devices. So let's build a model. Tiny is big. So now what I'm going to do is I am going to open up Google Colab. And I hope the browser window is visible to everyone.
Yeah, sir, Colab is visible.
Yeah. Okay. So we are here into the Colab, and I have already opened up the sine wave hello world program that we are actually.
Can you, sir, can you zoom? Govind sir, can you zoom little?
Yeah, let me just check that. Is it
Yeah,
readable now,
it's
sir?
there. Yeah.
Okay. So as usual, we have to import some model related data, and we are importing some library, machine learning library like TensorFlow, and we have done some installations like for Matplotlib, NumPy, and Math. So all that is already there. I've already run this. And as I said, we can select the runtime from here. And if at all I want to change, currently I'm not using any kind of an accelerator. So I can select, I will select GPU as my accelerator and just try to rerun all my cells. So I'll just rerun all the cells once. And to begin with, as I said, we imported some libraries over here. And here we are creating some sample data points for our sine wave. And we have used around 1,000 samples. And we are generating some numbers randomly so that we get some randomness for these samples. And that is what we are doing over here. And you can see there are X values that we have created and Y values. That is the sine wave that I said I wanted to generate. So this is actually creating the sample data points, and we are going to see the sine wave being generated over here. Because I don't have external data points, I'm generating the data points right inside this Colab. So let's wait till this runs. In the meantime, if anybody has anything to say, you can just have a word. Yeah. So what we have done is we have generated the sine wave over here. And this is a very clean sine wave that has been created. And this is our data point. It's extremely clean. Real world data is not so clean. You know that. So let's put some kind of noise in this. So over here, what we have done is we have put some noise. We have added some noise on that sine wave so that it becomes extremely noisy. And from that, we are going to create a model that's going to approximate this. Okay, so this is the program that's going to make it extremely noisy. And further up, and we have plotted it using matplotlib. Then further up, what we are doing is we are going to, as I said during that entire session, that we need to train our data, and generally the data set that we have, we split it up into 60% of training data, 20% of validation data, and 20% as test data. So here we are making that split of 60, 20, 20. This portion is actually doing that. And we are plotting that same sine wave with the different types of data sets using different colors. The data set that we have created over here, this noisy data set, has been split into 60, 20, 20. So over here, the training data set is in blue, that is 60% of the data, and 20% that is yellowish, and 20% that is red, that is validation and test data, so that we can make identifications between the training data, the validation data, and the test data. Then using Keras, we are creating a simple model architecture. Here you can see that we are using the dense layer, and there are 8 neurons over here. The activation is ReLU. And we are using the input shape of 1, that's a vector. And the final layer is again a one single output, because we are going to predict the sine wave output. So it's going to be a one single value. So we just have one neuron at the output. We are compiling this model over here. The optimizer is Adam, the loss, and we want to see the mean square error loss, and the metrics is mean absolute error. And over here we are training the model using the fit function. The X train and the Y train are your tensors, and the epochs are 500. The batch size of 64 is used. That means 64 data points at a time. And we are also using the validation data that we have created, the 2020, and that is being passed as X validate and Y validate. And the moment we started running this, we are running for 500 epochs, and you can see that it has started running the model. And finally, we are seeing that at the end of the 500 epochs, the loss is 0.1569, the mean absolute error is 0.3, validation loss is 0.16, and mean absolute error is 0.32. Now we would like to see this visually, so we are plotting this graph of loss, which is nothing but the distance between the predicted and the actual values during the training and validation. So there comes our matplotlib, and we have plotted this, the training loss and the validation loss. So this is slightly constrained. So what we are doing is we are skipping the first 50 data points so that we can zoom in onto the actual what we want to see. So we have zoomed in over here, and the same plot is plotted, and you can see the training loss and the validation loss being plotted in green and blue respectively. We have zoomed in a bit. You can see the scale has changed over here in both the cases because we have skipped some 50 data points at the beginning. Then we are plotting the mean absolute error, which is another way of measuring the amount of error in the prediction. This is your MAE and the training MAE and the validation MAE. Again, matplotlib is being used over here for doing this plotting. And finally, what we are doing over here is we are calculating and printing the loss on our test data set, and we are plotting it. So this is terrible. You can see that these are our actual data points, that is these blue in color. And look what this particular model has done. It has not followed our expectation. It's horrible. The error is extremely high. It's nowhere close to a sine wave. So the predictions are extremely bad. We cannot work with this. Or what we do. So we try to improve our model. Now, if you see this model that we created over here, it had just one layer and just 8 neurons over here, and directly we had the output layer. What we are trying to do over here is we are trying to add some more layer in it. The reason why this happened was the complexity of this model, the complexity of this problem at hand could not be handled by the model. And because of that, we got this problem. This prediction is way beyond our expectation. It's very bad. So what we are trying to do is we are trying to increase the number of layers in our model along with the number of neurons. And you can see there are 16 neurons over here, and we have added one more layer over here. This is the second new layer that may help the network learn more complex representations. And finally, we have the output layer, a single neuron, that is the dense layer. The reason is we just want one prediction. We want to know what is the sign value. So now this, I feel, should give me my desired result. And you can see here, we have changed the batch size to 64. So this is the second model. I told you, you will always have to do some iterations. So I've also created a second model. Now this was my first model and this is what I got. Now this is my second model. The rest of the things are same, and I run it again. And now you can see that the loss is 0.115, mean absolute error is 0.08, validation loss 0.01, and 0.08 is the validation mean absolute error. Now what happens is, again, I plot this using the graphs, and you can see that the training loss, the validation loss, the training mean absolute error, validation mean absolute error are both plotted over here. And they seem to be slightly better off than what we had earlier. So how is this model going to evaluate? What would be the outcome of this? That we have still not seen. So let's see that. That is what we are doing over here. We are evaluating the model with the additional layer of this neurons that we have added over here. 1 minute. Where did it go? Yeah. So we have added one more layer over here, and with that, what is the output? Oh, that's really good prediction. You can see that the actual values are plotted in blue, the predicted values are in red, and it's actually following the sine wave that we expected. So this was our input and this is our output. So with just addition of one more layer over here, we can see that this has performed extremely well. And also you can see that the batch size has been changed to 64. So this is not that I get out of some kind of, applying some kind of specific rules. You have to make the best assumptions and the best guesses and try to figure out what will work and what will not. Because in such cases, the focus is more on getting this model with minimal number of layers to work, so that you can fit this model onto the device that you're planning to load it to. Now, I know I have around 512 KB of flash memory because this model will take some amount of space, and along with that, I have to write some program or code for that board to make things happen. So even that code is going to count towards my flash RAM. Taking that into account and this into account, you should have good enough size of code that's going to run, and it should fit in that 512 KB that we have. So as I said, it's about iterations. Now I still don't know what would be the final size of this model. 1 minute, let me just stop this runtime since I'm not using it. Okay, so we are still not there. I know now that the model that I have created over here is a good approximation. It's a very good approximation, I would say. I'm getting a great sine wave over here, but I really don't know what's going to happen on the board. So now that the model is ready, I know it's approximating or giving me the true predictions that are very close to the actual. The next step is to create the TensorFlow Lite model. Now I've created this model in TensorFlow. I have got this. I've made it. Now I have to generate a TensorFlow Lite model that I'm going to port onto the board that I'm going to connect to my computer. So now how do we create that TensorFlow model? So for that, we use TensorFlow Lite. And the first step is convert the model to TensorFlow Lite format without quantization. I'll come to quantization slightly later down. But the first step is to convert the model to TensorFlow Lite. And TensorFlow Lite has a good amount of library to do that. So here we are actually using that library to convert that model into a TensorFlow Lite model, which would run on my board. So this is what is happening over here. And you can see that I have got a model size. It's showing me a model size of 2512. That's actually in bytes. So we have generated a model that's going to take up about 2.5 KB of memory. Okay. So that is what we have done. Now, once we have converted the model using TensorFlow Lite, the next step is to actually use an interpreter and allocate some memory for the model. Now what we are trying to do is we are going to quantize this model. We have this original model that's around 2.5 KB, and then we will have a quantized model. So we are actually going to create two models over here. One is the normal model and one is the quantized model of the sine wave. So for that, we have to allocate some memory for each model, and that is what we are doing over here with allocate tensors for both the models. One is for the quantized and one is for the normal model that is non-quantized. Then we are getting some basic indexes of the input and output tensors because we need to input the data and get the data at the output. So we are initializing some input and output tensors. Then we are creating some arrays to store the predictions for the quantized and the non-quantized model. And then we are running each model's interpreter for each value and store the results in the array. So here we are actually invoking the model. You can see the model invoke that's going to run the inference. And we are going to do that for both the models. That is, one is the quantized and one is the non-quantized. So the quantized model invoke is over here and the normal model invoke is over here. So this is what is going to actually make the inferences run over here. And then we are actually going to plot this. So what we see is after we have used TensorFlow Lite and the conversions have happened, the actuals are in blue, the original predictions are in red, and you can see the light predictions. Of course, they are not visible, very visible. They are in blue crosses, and green crosses are for light quantized predictions. So we are plotting all our waves all over each other so that we can see how good or bad the model is after using TensorFlow Lite. You can see it's approximating the sine wave beautifully. So we have the actual, that is our original data, then the original predictions with that data. Then we converted it to light, and the crosses, the blue crosses, they are being overlapped by the green crosses. That is the prediction of the light model. And after the light model, we have further quantized it and we are getting those green crosses. Now, what is it that we mean by I have quantized it? Basically, when it comes to TensorFlow, we are generally working with floating point numbers. And what are these floating point numbers? Where are they? And what are they actually, what do they actually mean? So basically, these floating point numbers are what we are going to work with in the model. So these models actually work with floating point numbers when we are working in TensorFlow, and they are 32-bit. Now, working with these numbers, 32-bit in Google Colab and on desktops or powerful machines is going to be easy. There's no problem. But when you move it to a device like what I've shown you, it's going to eat up a lot of memory. So we convert these 32-bit representations into 8-bit integers using quantization. Now, many of you would argue that if we do that, it's going to lose accuracy. Some accuracy is sacrificed, but they are extremely optimized. Thus, it has been empirically proved that the loss that happens will not affect the performance of the model. And that is the whole basis on which this is based. So after quantization, what is going to happen is, you can see we have given you a metric over here. The basic model was of 2736 bytes. That is after we applied the TensorFlow Lite conversion to the basic sine wave. So the model that was created was about 2.7 KB. But after applying quantization, it has reduced to 2.5 KB, that is 2512 bytes. That is a huge saving of 224 bytes. Now, many of you who are from the high-end computing background, you would say, what is 224 bytes? But for people like us who are from the embedded background, 224 bytes is good amount of memory that I have saved for a small device. So this quantization step is extremely critical, and it's advisable that you apply it. It's definitely going to save some good amount of memory for you. And trust me, when the number of layers go on increasing, this quantization is going to actually save lot of memory, because imagine how many 32-bit representations you would have in a huge model where we have just 2 layers, and that's saving around 224 bytes. So all that 32-bit representation is going to be converted to 8-bit representations, and these representations are actually, I mean, it's 4 times the saving. So the amount of memory that you're going to save with quantization is great, and you can see there is no difference much that you can see in the quantization, after quantization, in the outputs of this. Okay. And one more thing that I would like to say over here is many of you have actually seen this at work during your during your FDP, like what are the different kinds of activations that are applied, and what kind of how the neuron is activated, and what is ReLU and all. I think you must have certainly seen this. So this is all about, how what kind of optimizations you're going to use, what kind of input data that you have, how you have designed your input data. I've been talking about that very much during this entire session. That input data is also very critical, how you have created it or how you have used it. Okay. So Y-train is nothing but it is the training data set that I have. And as I said, what is the output? It's Y is equal to sine X. So Y is the output of the sine function. Somebody asked what is that Y-train? So it's the training data that I have. So that is, yeah. Yeah, can you ask me the question? Somebody is putting up some question. It disappeared from my screen. Okay. Fine. I think the question, I think that I answered that question. Okay, fine. Yeah. So now the next stage is we have quantized the data, and now I'm happy with the way the model is created. And hello, am I audible?
Sir, yes, you're on.
Yeah, yeah, yeah. So I quantized the data, and finally I have this quantized model. And the next step now is to actually convert it to some kind of a file, which is a flat buffer, so that I can load this into my microcontroller. And to do that, we have this xxd command that I have in Unix, and we're going to convert it into a flat buffer file using it. And finally, the model that is generated out of this conversion, this xxd, is going to convert it into that flat buffer file. And this is the model that you see finally. This is the model that I get after the conversion into a flat buffer file, and this is what I am going to load into my microcontroller. This represents my model. So all this has been done in Colab, and you can see it is nothing but a combination of huge number of hex equivalents, and all this is what I need for my microcontroller. All those who are from the embedded background would love to see this, because this is what they see generally when they see their memory models. So this is what I wanted, and this is what I've got after the conversion. Now my job is to take all this data, or rather this file, and this is the length of the file that I have, 2512, and take this and put it up into my IDE, where I'm going to do the development for my embedded board. So now I'm going to go over there. So it's time to move on to that. Remember, I'm going to pick this up, copy it from here, and put it in some file. I'll show you that file in that particular embedded board. Okay. So now I am going to share that thing with you. Just hold on. Let me just open it up, and it's time to connect the board. And this is the board. I'm going to program this. I'm going to connect this to my computer. Okay, I'm just launching it now, and then I will share it with you.
Show this board now. If you remove your sharing,
Yeah, I do that.
sharing that, yeah, then it will be a full screen. Only you and the board will be visible. Just one question. Up till now, whatever you are done in Colab, it is independent of the board, no?
Yes, it is purely TensorFlow and TensorFlow Lite. Why we are doing this is we are actually, whatever models we create them in TensorFlow. They are neural networks. And once we have the model ready, that is the normal TensorFlow model, that model we are converting to TensorFlow Lite, because we want something called as a flat buffer file. And that TensorFlow Lite model will then be converted into a flat buffer file that I have shown. This is the last thing that you're seeing, all these hex numbers. They are actually those, that's the flat buffer file. And that file, it's representative of your model, which we are going to load into the board.
So board can be any board now after this.
Any board. That is any board you can use, except that it should have that much amount of memory, and at least some amount of static RAM. This is having around 128 KB of RAM, because it will need some scratchpad area to do some basic processing. So I don't know whether this would really work on an 8051 with minimal memory requirements. I have not tested it, this was the board that I generally use, and the other one that is that's MSP432 from TI. But again, actually getting this into that environment is slightly involved. What kind of IDE you are using? And now we are using Cube IDE over here. I have not tested this with the TI's Code Composer Studio, but it should work. There are people who use that also. And you can port this to even a Raspberry Pi or any kind of a board that's having minimal hardware, requirements. It's going to work over there also. So, Abhi, एक problem I'm getting is I'm not seeing my sharing. Sir, what did you say? किसका share निकाल दूँ?
Then if you are showing the board, no, if you want we to see, then
I will do that.
Okay. Sharing, no, then only your video. When you speak in that case, on full screen, we can see you and the board. It's like that.
Okay.
If it is shared, no, then it comes as a small window at the corner. It may not be visible the way we want. Yes, it's like that.
Okay, fine. What I'm doing now, I don't want this my web browser to be shared. वो sharing जा नहीं रहा है web browser का मेरा.
Then remove the sharing, do it again. That's it.
Can you see this IDE, Cube IDE?
Yes.
Everyone?
Yes.
Yeah, great. Okay. So now we are into Cube IDE, and the IDE that is used with STM32 boards, and this is the place where we are going to do our development for the microcontroller. So to begin with, first let me show you that we have this data over here, and I have this sine model you can see, and this is the model that, 1 minute, let me just scroll. Yeah, this is my actual model. I've commented that out because there I was getting 2552, some error had occurred. So this is my actual model. You can see I have picked it up from there. This is that same thing, same file, the flat buffer file, and I've brought it over here. It shows the model len as 2512. So I have this copied over here in my IDE. And
it's some file is.
Sorry, your voice is cracking a lot. How do you get this?
How do you get this from the Colab to the IDE? Only copy paste, direct copy paste?
Yes. Just copy paste. Just select it over there and Control C, copy it. And first you can paste it in Notepad so that you can see that there is no formatting that is there. And then from Notepad, you can pick it up and put it over here and create a simple CPP file over here through the source editor. And that's it. You just paste it over there. Nothing. There is no special import requirement over here. And of course, when you're creating the project, you have to ensure that you set up the necessary paths and all. It's quite an involved process. Every IDE has got a different way of doing it. So for that, you need to read the user's manual or the help from that IDE to ensure that TensorFlow and TensorFlow Lite models, basic libraries are properly, imported. So in main.cpp, you can see that there are a lot of imports over here from TensorFlow Lite. So these have to come in properly. So there are a lot of settings that you need to do in your IDE, and all that is documented in the help section. So this is the only little glitch that many people face getting this correctly configured in IDE. And the sad part is it is different for different IDEs. There is no standard way of doing it. So the only problem is getting these libraries over here, because these are the libraries that you get on GitHub for TensorFlow, and from there you have to get them over here. So that is the only glitch. And then we are into a normal embedded domain, and all this namespace and extern float, all this over here. You can see that I'm using the 2πf formula for creating that sine wave. How to basically for showing it on the board, plotting it over here. And here you can see the TensorFlow Lite basic libraries being used. And this is all documented on Google. So you can straight away refer that. We will not get into the details of that because, again, that's quite an involved process of understanding how these things actually work with the embedded board. So, and most importantly, every board is different, so it's different for different boards. So you have to figure out those things. There is no standard way of doing it. The next is I will speak about the board now. What we have done is I've just configured its UART. I have configured the init timer and init GPIO. Now, if anybody has used STM32 from the embedded world, you might have used the ready-made code generator. What I've done is I have not used the code generator because it produces a lot of unwanted code that can add a lot of unwanted stuff to your program, and that will increase the size of your code. So to remove that unwanted code, what I have done is I've just used the visual configuration tool from STM, and I configured only two devices over there, and unwanted code was removed. And after that, only the code for initializing the GPIO, that is the input output of this board, and the timer and a UART, because I have some plans of actually plotting this to the UART, which I have not done still. So I've just kept that. And the HAL init is the basic initialization routine that is given by STM people. It's the library of STM32 for initializing their basic functions of the board. So that is to be called first. And then I have initialized my general purpose IO GPIO pins using init GPIO. And that is right over here. Yeah, here. So we are using the LED pin for actually pulsing the LED. And then I am using the mode for alternate function in push-pull configuration. And there is no pull-up that is used. And I'm using a low frequency pin. And on that pin, I am going to do pulse width modulation. So I'm using a timer that is configured on that pin using timer 2. Of course, these are specifics of the board. You would not understand much into this because unless you read the library or the library of the board, you will not follow. But in general, what I've done is I've configured the input output pin to function as a pulse width modulated pin. That is what I'm doing over here. Okay. And then we have the timer over here. Now, how the pulse width modulation works is this is, as I said, 16 megahertz. I've configured it for 16 megahertz clock frequency. And as per the manual of this board, it says that once you, I mean, the prescaler, the default prescaler for that frequency or any frequency that you're going to use is going to be 800. So I've kept the prescaler at 800. So if effectively you need 50 microseconds for one timer increment. Okay, and the period that is the period of this wave is 10 milliseconds, and it's going to be in the counter is going to be in the up mode. And you can see that I have used one variable called as fadeness over here, and it is actually how I'm going to pulse that pin using this fadeness value. Now, what is this fadeness? It's over here. You can see that after I pass on that model, the model is actually picked up by this particular code over here. Let me just see where that file is reported. Where I've recorded the file. I'm not able to locate my reportage. Where is the file? Because that
गोविंद
file,
सर,
हाँ
वैसे भी आप ढूंढो मत, क्योंकि वो हम लोगों को वो कोड में तो लॉस्ट हो जाएंगे।
नहीं नहीं, सिर्फ वो फाइल किधर है उतना ही मैं देख रहा था। एनीवेज ठीक है, पर द बॉटम लाइन इज the file has to be imported over here, the file of your model, so that the code can take that file and start working on it. So once that file is over here, what we are doing is we are taking the tensor values of that we created the input and output tensors over there. They are actually stored in this x value and the y value, and we are actually working with that y value, and based on that, because that is the output of your sine wave, so that y value is going to produce that data point, and that data point we are giving to this fade variable. We are storing in the fade variable using this expression over here. That's going to produce this sine value on this board. Okay, and that value is passed to the pulse width modulated pin that is over here in this pulse. So you can see that I'm passing this value over here in the init time of fade, and that's what being passed over here in this. Okay, so float fadeness. So this is going to actually create that function of sine on our board. So now what I'm going to do is I'm just going to compile this first. So I've hit the compile button, and I hope everything goes on fine. Okay, so the build has finished, and it's compiled now and ready to run. And I'll start first. Let me just go into the debug window. So I'm clicking on the debug over here, and I hope all things are fine because there are a lot of things that are involved in this. In the meantime, let me just see if I can. Okay. It's still doing it. Okay. So now what I'm going to do is we are going to plot that sine wave that we have generated using this model over here. Okay. And it's going to actually go to pulse this thing. And I'm just going to start this now. I'm starting the trace. I'm clicking on the trace now. And now I'm actually starting I'm making this code run over here. And there it goes. You can see that the same sine wave is being plotted over here. And it's being generated on the board. And you can see the board. 1 minute. I think it's very bad. Video options.
गोविंद सर,
हाँ सर, मैं उसका ये निकाल रहा हूँ बैकग्राउंड।
वर्चुअल बैकग्राउंड निकाल दीजिए ना।
हाँ निकाला।
जस्ट रिमूव द वर्चुअल बैकग्राउंड।
कैन यू सी दिस? हाँ. See, it's pulsing the LED, and the way your sine wave is progressing, you can see how it's dimming and it's working. Can you see this, all of you?
ग्रीन
So it's
ग्रीन एलईडी नो?
following. Yeah, the green LED. The green LED. Yeah, there it is.
यस यस।
It's pulsing it. So we created that sine wave data points. We didn't have the data points, so we generated the sine wave data points in our TensorFlow model. We trained the model to approximate that sine wave. Then we converted that model into a TensorFlow Lite model. Then we quantized it and we got a flat buffer file. That flat buffer file, I got it over here, and I wrote some program to use that flat buffer file to create this sine wave and a pulse and LED using pulse width modulation. So this is how we have actually ported a full-fledged ML model onto a small board, and that is TinyML for you. Okay, so I think that sums up the idea of TinyML. And if this works on a 512 KB, yeah, somebody is asking how big model can be converted. So I said that that's the key point over here. That that depends upon the problem at hand. Now people have successfully run even image classification models on such boards. Now it all depends upon how you have trained your model, what are the data points, how well it is trained, and how much amount of data you are actually putting in there. So that it all depends on the design. And when you start, as I said, always start off with understanding what data is needed, how much amount of data is needed. Just don't go on putting up things or data that is redundant. So there are a lot of things in this that go into the making, but the bottom line is whatever you can do on a GPU or a TPU, you can do all that on these small little devices using TensorFlow Lite and correctly writing the code on the embedded side so that that code is also minimal in size and everything fits onto the memory of that board. So I think that's the end of the story. And finally, I would just say Tiny is big, and it's going to be really big because all these devices are everywhere. All this data, if you can just pick up and you can process and create applications, this is really going to take a big shape. And you can see the effects right now. It's already happening, and it's bound to happen further. Okay, so I think that's it for the day. So,
Yes, I'm here. So
yeah,
TinyML basically is a kind of a it's an idea to put ML model onto a embedded board.
any
That's it.
device, any small device. Nice,
Any
sir.
small device.
It's already people have started working on it, and you can see now slowly more devices will come in the market. And basically image classification, which is generally the forte of webcams or cameras of mobile phones. Generally, we connect to the data center to do all this ML, but the interactivity is lost because you need to connect to the internet. Your bandwidth should be high. If you don't have the bandwidth, things don't work. Then the amount of time it takes for the data to go over there and come back, that latency is there. At times, latency is not permitted. You cannot have that kind of latency. So, I mean, then in that case, what do? Create such devices. And as I gave an example, like you can even have devices like you can put devices in the chappal and really create chappals that are extremely comfortable for people who have problems walking with specific chappals. So customization of such kind of things, customization of small sensors that could be there on the body. All these sensors can actually run machine learning models using this. So that's the basic idea.
Yes. Yes, microelectronics. You also tried some other boards any time, like very good application on PSOC, no? Board because PSOC has so many other onboard
Yes, sir.
facilities
Yeah, you
available.
can work it on. So, see, when it comes to selection of the board
Yes.
is immaterial because what you need to put into the IDE, I mean, what libraries you need to put in the IDE from TensorFlow Lite, they are standard. So you have to just import those libraries into your IDE where you're going to develop your embedded application and set them in the correct paths. Once that is done, then it is purely an embedded application.
Yes. So those libraries, we will get it from where? Like it will be from
From
the
GitHub.
vendor of
Yes,
the manufacturer,
TensorFlow. No,
or
no, TensorFlow. TensorFlow's GitHub library has TensorFlow Lite models, and they have
okay.
created some basic, sample projects for some standard IDs, not for all, but for some standard IDs. So you can pick up the sample project with all the imports being done for you, and then you can start off from there. पीसॉक के लिए मैंने देखा नहीं है सर पर कील के लिए दे हैव मेड कील इज देयर देन I think for Arduino there is support. They have created some support for Arduino. And there is, I think, something for MATLAB also. It's there on GitHub.
Okay. Okay.
It's only वो जो critical उसका problem है, that is, it's not a problem. You should be able to correctly integrate when you do these imports, these includes. Most of my time was lost in this because it was not finding the correct libraries in the system. So then
It's
yeah, so basically this is CubeID works on the principles of our what is that ID, the most common Eclipse. It's based on Eclipse. So using Eclipse manual, I try to understand how this is done, how to do the imports correctly, because this is from the third party. So integrating that into this ID is the only problem. So I had to read a lot to actually do only this much. The rest is pretty straightforward as far as embedded is concerned. So that is the only challenge that I had. But yes, you can do it for any device.
okay.
I'm very sorry, I may not be able to share the code of embedded. Somebody is asking me to share the code because we are going to work on this, and I've just given you a test case. Now we are going to do something with this. And we are also into training, so we are going to set up some kind of training on tiny machine learning using embedded. So I'm extremely sorry, Dr. Chetna. I may not be able to share this embedded code with you. So please excuse me for that. Anything else? Uh, so I hope it was you enjoyed the session. Most of the talking I did because when if this was a face-to-face, I like interactivity, but when it comes to online, having that interactivity is really difficult. So I was just talking and talking. So please excuse me for that. And there is a lot of thought involved in this. So if I lose my track, I may just go off track. So I thought, let me just talk. At the end, I may ask people if there is anything that you would like to know. So if anybody has anything to ask or anything to know, I'm there right now. We have 5 minutes left.
Uh, you want to say something? Anything
No,
you
no,
want to say?
nothing. No, not from my end, from the participants'
Okay.
end. If anybody has anything to ask or
No, no, they
share.
are typing they are typing thank you. It means that it's a
Oh,
lifetime.
okay, okay. Okay, sir.
Okay.
No
So
problem.
Govind sir, thank you very much. Your session was really our objective has been fulfilled.
Yeah,
I said that we want it has to be an interdisciplinary approach and
yeah,
particular domain specific, and that's what we want to show and demonstrate various. We had an
yes,
yesterday we had an on healthcare. Then driving. Pawan sir has
yes.
demonstrated today again evening he will be actually going into details of autonomous driving, and today
Okay.
you
Oh,
have
great.
shown how exactly it's a handshaking between the collab and our
Yeah,
employees. That's what you actually demonstrated, and
yeah,
you started from the basic the actual demo on board.
yeah.
It was a very great thing. It was a nice thing, and that's what I was expecting. Because now I can see it has opened up Pandora of projects. At least
Yes,
I am concerned as a faculty member. It has opened for me a new Pandora of at least mini projects, minor projects, which we give to our students in third year. Now there
yes.
it is a possibility of having interdisciplinary projects. I can have a computer student writing entire model into the Colab, doing the stuff over there, and I can have in the same group one electronic student working on a board and making a real life application feasible. So it has opened new concepts and new things for me. So thank you very much for this session. And tomorrow you will have an entire 1 day session. So
Yeah,
now
that's on IoT. IoT.
that's on IoT on Edge, and probably
That's going to be very challenging for me because I have to deal with the entire flow from the board to the cloud and from the cloud to the board. And we are going to use IBM Cloud for that.
yeah. So
So,
tiny to big, big.
no,
So
and I would
that
like to add one thing finally before we end. I believe now it's time that electronics engineers are going to have some great time in the near future with TinyML, because this is going to be the future, and TinyML machine learning is actually going to shift over to TinyML. And Google is betting big on this. They are investing heavily on TinyML, on TensorFlow. So electronics engineers, where people are saying that there is no, scope for electronics engineering in India, trust me, this is going to be the game changer. And with electronic vehicles, autonomous vehicles around the corner, this is going to be big. So I think electronics engineers should focus on this, and it is only they can do it ultimately on the embedded board. And learning machine learning is not a big task for anybody. So they can have the best of both the worlds and really make it big, because IT people will not be able to work on embedded boards. They have to really slog it out. Electronics people have been working on it since the very second year of their engineering. So it's great. You should exploit this field. That's what I would like to say. And thank you very much, all of you, for your patient hearing.
Yeah, thank you, sir. Thank you very much, and looking forward for your tomorrow's session again.
Yes, certainly, sir. I would be
Yeah,
happy to join. Yeah.
yeah.
Thank you very
Thanks,
much.
man.
Yeah. Yeah.
Thanks a
Bye
lot.
bye.
Thanks. So,
Bye.
okay,
Take
bye bye. Thank you, participants. Will session 5 o'clock with Pawan sir will be there, taking us on the autonomous car. Let
Okay, sir.
so
Bye bye.
yeah, chalo bye now.
Yeah. Yeah.